in the last session we stopped at high powers. So with the lasers we can generate high powers, so such as like milliwatt to megawatt using CW lasers. With the pulse lasers you can generate from giga to hexawatt. So now it's different applications, you will use different powers. So for example, right, in the laser printers or in the CD writing or reading, you doesn't require like high wattage powers. So maybe very few milliwatts is quite enough to write or read in the CDs or DVDs. So there you require a milliwatt laser systems. Okay, so the reason we already discussed why these CW lasers can be focused very tiny focuses, so that it can store the data in very small areas. So the conventional source cannot do that. So that's why we have wide variety of lasers with the different powers. So we use depending upon the applications what we are looking for. So now we have the ranges from milli to hexawatt. So you can choose for the different material processing and for the military applications and for nonlinear optical applications. If you want to do any nonlinear optical phenomena or processes, you need to have a high power lasers. So we generally use high power laser systems in a nonlinear optics. For example, like a pulse lasers will very suitable lasers to do nonlinear optics. Okay, so now one can calculate the power using this formula. Your P equals to energy per time. If you take the average energy of the pulses, because your laser system has many number of pulses, so you can take the average energy with respect to your time. You can also sometimes you call the repetition rate. Okay, so the repetition rate will tell you number of pulses per second. So this gives you your power, so energy per time. So if you want to calculate the peak power, so what is meant by peak power? The peak power, you have a pulse, so then your peak power at the peak. So if you can calculate the peak power, so that gives you, for example, you have a 10 millijoule system and your pulse width, so your energy per pulse is 10 millijoule and your pulse width is 1 picosecond. Okay, that gives you your peak power. So that now if you calculate your peak power, you will get 10 into 10 power minus 3 joules, and your 1 picosecond it's 10 power minus 12 second. From that you can calculate, it becomes 10 power 7. Your power becomes 10 power 7 joules per second. Okay, so joule per second is nothing but a watt. Your power can be calculated in the watt, so energy will be in the joules. So now joule per second is nothing but watt. So now you will get the peak powers of order of 10 power 7 watt. So here you will get, this is 10 power minus 2 by 10 power minus 12. Okay, that is almost your the peak powers in the order of 10 power 10 watts, right? Yes. So this is the peak power. You can see, you imagine, like even you come up with a millijoule pulse, now you are able to get 10 power 10 watt because of your pulse duration. You have a peak powers. So this is the peak power at this position in the pulse. So that gives you very high peak powers. So that creates huge electric field strength at that time. Okay, so that we will see. So now if you have you can calculate the intensity of the light. So that is one of the quantity you generally measures. So that is nothing but your power per area. For example, now you have 1 watt power, you are focusing down to 2 micrometers. Okay, so now your focal spot having 2 micrometers. Okay, your focal spot in general it's a 2 omega naught is representation. So you can calculate the intensity. So 1 watt system by pi omega naught square, it's your area. So that gives you 3 into 10 power 7 watts per centimeter square. So that is a huge intensities from the laser systems. So this is where one can calculate the power as well as intensities. Okay, so now we know that your intensity is proportional to your electric field, the square of the electric field. Okay, so in principle your intensity is equals to, with some constant, you remove the proportional constant, there will be some constant with respect to your refractive index of the medium and the speed of the light. So that gives you your NC by 8 pi modulus of E square. From this you can calculate the electric field once you know the intensity. So because you know the power of the laser system, how much power you are using, from that you can calculate the intensity, how much area you are focusing or you are using. From that you can have an intensity value. That intensity value in terms of megawatts per centimeter square, you substitute here, you can get your electric field strength in terms of volt per centimeter. Okay, so this reminds you that your hydrogen atom, in a hydrogen atom, your electron experience the electric field strength in the order of 10 into 6 into 10 power 9 volt per centimeter. Now you want to perturb the electron, you see you have to be comparable electric field strength you have to use. Okay, so to do that you can calculate how much intensity is required to perturb your electron in the hydrogen atom. And similarly with the different materials and the different atoms, the electric field strength changes because the electron feels the different interactions, different electric field strengths from the different orbitals. So if it is core electrons, they have high electric field strength associated with it. When there is an electron in the valence band, or you can say outermost electrons, they feel less electric field strength. So to perturb these electrons, to excite these electrons, you need high electric field strengths. For example, you want to remove the electron from the material. Okay, so all this requires high electric field strength. So now accordingly you can calculate what is the electric field strength you require to make a transitions or any kind of a nonlinear process. So you can estimate the electric field strength using this formula. If no questions, we can continue. So now we will discuss about the high advantage of the lasers. It gives a wide tuning spectral range and also a huge spectral coverage. Okay, so now we see this is your electromagnetics radiation. So that is the spectra of your electromagnetic radiation. It ranges from radio waves to gamma rays. Okay, this is your electromagnetic spectrum. So now you have lasers in the wide variety of ranges which can cover most of the spectral regions of the electromagnetic spectrum. So lasers will cover from infrared. Okay, these are the different lasers having a tuning ranges. So with the different lasers you can see these are the tuning range for the one laser, and couple of lasers having tuning range of like this, and some lasers having a tuning range of, this is towards the frequency. Okay, so this electromagnetic spectrum is increasing towards this direction, is a frequency increasing direction. Okay, So now this is the tuning rays from the lasers, some of the lasers which covers the near infrared region. So these are the mid IR, and this is far IR, and this is coverage of near IR, and this is your full visible spectrum. So now we have lasers which covers the full visible spectrum, and also UV lasers and deep UV, and you can call vacuum UV, and you have a soft X-rays, and you can go up to almost mid X-rays. And still now research is continuing to extend this direction. Still research is continuing. So now still we are able to generate X-rays using lasers. So now this direction it already covered. So we have maser. So your maser is the first device which is used by stimulated emission of radiation. Okay, afterwards the laser comes. 1960 lasers, but around 1958 the maser come. So maser will work in the whole spectral coverage of microwave regions. So maser means microwave amplified stimulated emission of radiation, and also the stimulated emission emitted radiation, the amplified stimulated emission radiation for the radio is also there. Okay, so that covers the almost, we are completing the almost electromagnetic spectrum. Okay, so still there is a spectral range is not covered this region. We will see most probably in the coming years or in the future we will cover this spectral range. Okay, so that finishes your tuning range of your laser systems. So now we have a wide spectral ranges, and even each laser is capable to having certain tuning ranges. For example, now you see your CO2 laser can cover almost this range. So that means in the mid IR range it can cover the spectral range, maybe 9 to 11 micrometers. Your CO2 laser having a tuning range, and also in the krypton having a tuning range of your visible region, and dye lasers can be tunable from your visible wavelength to near infrared, and argon laser in middle of the, it's almost like towards the NIR region, but it's in the visible spectrum, like around 500 above to around 700 it can cover. So that is our argon spectral coverage. And excimer lasers, mostly these are the UV lasers you can call, it covers from your 400 nanometers to 200 nanometers. And you have a diode lasers which has a huge tuning ranges. It covers from 600 nanometers to almost end of your infrared spectrum. So you have diode lasers, and there are lasers called QCL, quantum cascade lasers. So these lasers which can cover from mid infrared to terahertz regime. So that means the terahertz regime is the part of the regime in between your microwave and infrared. So there is a small portion that is called 0.1 to 10 terahertz. In principle 3 terahertz is actually people call terahertz regime, but you can consider 0.1 to 10 terahertz. So this is the region in between microwaves and the infrared. Okay, so these quantum cascade lasers can cover from mid infrared to terahertz regime. And for the deep UV and vacuum UV and X-rays, higher harmonic generation is a technique can cover up to X-rays. You have a higher harmonic generation lasers which can cover up to X-rays. So now this technology is progressing, so we may move in this direction. Okay, so this And apart from that, we have other lasers with narrow bandwidths, narrow tuning ranges like NDR. You have a specific wavelength of 1064 nanometers or 1.064 micrometers, and Hini laser most operating wavelength is 632.8 nanometers or 0.632 micrometer, and Ruby laser, which is at operating wavelength at 0.694 micrometer, and there is a Tisafire laser systems which operates from 750 nanometers to 950 nanometers or 0.750 micrometers to 0.950 micrometers, and fiber lasers. So these are the now current technology. Lasers are developing. Your gain medium is fiber. Okay, so now these fiber lasers are the current technology. So now currently these fiber lasers are operating wavelengths or tuning range from 1 to 2 micrometers. Okay, so this is possible with the active medium. Now with the nonlinear optics, or nonlinear phenomena, see now it's a compressed format of your electromagnetic spectrum, but you have lot of gaps in between the spectrums. There will be a lot of gaps, so these gaps will be filled with the your nonlinear optics. So you can generate, taking a one wavelength, you can generate multiple wavelengths using your nonlinear optics. That we will study how we do it. So currently with this current technologies, you have all this spectral coverage without a gap. You can create without a gap all this spectral coverage. This with your measures you can cover this region. With the optics, with the lasers, you can cover this region, and this region still with the lasers, with the stimulated emission of radiation, it's not available so far, but we are keep continuing. Our researchers are working towards the developing the lasers in this region too. Okay, but with the current technologies, we have all the wavelengths in this region without any gap. So we have the different techniques, optical techniques are available to generate the wavelength whichever you want to study. Whole phenomena using nonlinear optics and different laser systems, we can cover the spectral regions from infrared or from terahertz region to almost your X-ray region. Okay, so that is about the tuning range of the laser systems. So the applications, to have a specific atomic excitations or molecule excitations, you need a specific wavelength with this narrow bandwidth. So that you can use from any of your laser systems, which gives your precise atomic precise wavelength to have a atomic excitation. And you can do laser spectroscopy, and you can use these lasers for the medical applications and to study different medium you want to study, like the laser propagation. Like for example, like air pollution you want to study, you can use selective lasers, or also in the fluids you want to study. So with the different mediums you can choose different wavelengths. For example, our human body absorbs IR radiation. Okay, and it responds very nicely to the IR radiation, so that your IR imaging can be done using your IR lasers. So each laser having different advantages, each wavelength of the laser has different advantages. So depending upon your applications, you can choose a laser from this a bin. Like you have a big bin, so that means you have a basket of lasers you can choose for your requirement. So now all the wavelengths are available for us to study whatever the physical phenomena or the applications you want. Okay, so coming to the other characteristic feature of the lasers, so you can generate laser pulses to very fast. So that means you can make a ultra short pulses. So for example, your pulse width in the nanosecond region, you call a nanosecond pulses. your pulse width is 10 picosecond, then you call it's a picosecond pulses. So we can generate femtosecond pulses. So till 2000 and 2010, so we are in the regime of femtosecond pulses. The technology is at femtosecond pulses. Now in the 2020, we are in the regime of attosecond pulses. Okay, so we are able to generate attosecond pulses. Now this is the shortest pulse available in the current technology. So why these short pulses required? These short pulses have huge advantages. For example, to study a fast process in a material system, or any fast process you want to study which can interact with the light, can be studied using these ultra fast lasers. And to make a like optical clocks, the optical clocks are very precise. Okay, and optical computers, and for any imaging techniques and high resolution radar signals, you need these ultra short pulses, are called ultra fast pulses. Okay, so now we almost finished the different characteristic features of the your laser pulses or your laser characteristics. Okay, some of them are similar like high power and high intensity, having a same name, but having the same power, you can make a high intensity, because when you focus into a small region, your intensity becomes huge. Okay, so these are the major advantage of the lasers with their characteristics. So now I am going to different cavity modes in the laser oscillator. Okay, so now you see this is the laser cavity. So your two mirrors creates a cavity. So now oscillating, what is cavity modes? In general, the cavity modes are the frequencies which are oscillating inside the cavity. So those are you call cavity modes. So that means not all the modes can exist in the cavity. Only a specific modes will be allowed to oscillate within the laser oscillator. That's why we call laser oscillator or laser cavity. So laser oscillator means these modes are oscillating inside the cavity. Okay, so now always, so this is the one of the mode. You can see always the nodes will form at the end of the cavity, end mirrors like this, here and here nodes will form, and the antinodes you can see. So to have a mode to sustain in the cavity, it has to fulfill this condition. That means the wavelength has to exactly fit in the cavity, otherwise they will cancel out. So why so? That means when you have two waves add up, you have to interfere constructively. To make a constructive interference, these modes should oscillate such a way that it has to fit the wavelength, otherwise it doesn't form a standing wave. If there is no standing wave formation, that means those waves or these modes will interfere destructively, the amplitudes will get cancelled out, so this mode vibration will not be there. Okay, to have mode to sustain, they has to interfere constructively when there is a reflection back. So this means this wave, for example, it's from here to here and coming back to here. Okay, that is oscillating from between two end mirrors. So this has to oscillate continuously. Okay, then you call this mode is sustained in the cavity. Okay, to have the mode to sustain, it has to, the wavelength should fit in the cavity. Okay, so now for example this one, this is one more different modes. As you see, as modes are changing, now always node formation should be at the end mirror, so that gives you a standing wave formation. So now you can have different positions, nodes and antinodes, but always at the end mirrors you should have a node formation. Those modes only will be oscillate in the cavity, other will be cancelled out. because of the destructive interference. Okay, so now we go one by one slowly. First we go to the lowest mode possible. So now this is our cavity with the length of L. The lowest mode possible is this one. So this is your standing wave formation. So now your length is equals to your lambda by 2. So the lowest possible wavelength is your lambda by 2. Okay, so that is nothing but your lambda is nothing but your length 2L. So your lambda 1 is nothing but 2L. So now the frequency of the mode is nothing but, the frequency is nothing but velocity of light by wavelength. So from that you can calculate your mode frequency is nothing but C over 2L. Okay, your lambda is nothing but 2L. So your frequency, the lowest mode possible frequency is C by 2L. So now you see this is your frequency. So we know that there is a width associated with frequency. Now you see this is for your line width. The line width is actually from your atomic system or molecular system, that gives your line width. Then there is one more width increased because of the cavity. Can you tell why this width is increased when you place your photons in the cavity? Anyone can answer? See, from the atomic, your lifetimes, you have a certain width associated with. That width is you call a natural line width. So that is the shaded region, like a blue color shaded region. Now when this photon is oscillating in this cavity, the bandwidth is increased, the width is increased, the frequency with delta nu is increased, right? Can you tell me why this width is increased when you keep the photon inside the cavity? So due to the loss in the cavity, what happens now, your photon is oscillating back and forth. These mirrors are not 100% reflective, so you always have loss. So that means you have a decay, so your oscillating frequency will decay. Okay, when it decays, this gives you a width to it will increase the width of your oscillation, that gives you your frequency becomes broadened. Okay, so that is because of the losses in the cavity. Whether these losses due to the medium or the reflection, so there are different cavity losses. All these losses will increase the width. That means your frequency width increases. That means your spectral width changes. I will stop here. We discuss more in the next class about these cavity modes.